A performance verification check, or PVK for short, is one of the most important activities a HUGO field service engineer performs, and is not a basic functional check and is not optional. A PVK is a structured, documented process designed to confirm that the HUGO system is operating exactly as intended before it is released for clinical use. From an engineering perspective, the PVK represents the boundary between the technical support and patient safety. Once a system has passed PVK, the clinicians trust that it will behave predictably during surgery so that there will be no issues. And that trust is built on the engineer following every step accurately and without any shortcuts. In this presentation, we'll walk through what a HUGO PVK actually involves, why it exists, and what engineers are really checking at each stage. I'll do a brief overview on each one and won't go, regarding the limits and tolerances, as that could lead to an hour-long video. The goal is not to memorize the steps, but to understand the intent behind them. When you understand that intent, PVKs become clearer and far more meaningful. Why do PVKs exist? PVKs exist because robotic surgery systems are safety critical devices. A fault that might be acceptable in other equipment can have a serious consequence in live surgical environment. And the PVK is designed to reduce that risk to the lowest possible level. From a regulatory standpoint, manufacturers are required to demonstrate that systems perform within the defined limits. And the PVK is the field level confirmation of that requirement. It provides documented evidence that the system meets performance and safety specifications. For engineers, the PVK is not just about catching obvious failures, it's about verifying subtle interactions between the subsystems within the HUGO robotic system that might be unnoticed. That's why PVKs are very detailed and they're very methodical in how they approach the whole system. When is a PVK required? This is required whenever the integrity of the HUGO system could be questioned by clinicians. Whenever they might suspect something could go wrong, a PVK is required. This includes new installations, major corrective repairs, any software updates, or of course when a component gets replaced. Let's say the arm gets replaced, this could affect the system behavior, so a whole PVK is needed. And the purpose is consistency. Regardless of why the system was serviced, the PVK ensures that it always returns to the same known working state before being used on patients. For engineers, this removes ambiguity. You're not relying on judgment alone. And the PVK, these documents, provides a very clear approved framework that defines when a system is safe to release. So this protects the patients, protects the clinicians, and it also protects engineers alike as well. Preparation. This is a very critical part of a successful PVK. Engineers must ensure that the correct tools, the testing equipment, and documentation are available and they're all in calibration where required. Rushing preparation of these variables increases the risks of errors later. So it's always good to be prepared before you do a PVK on an equipment. The system must be fully configured exactly as it will be used clinically, as if it was to be used in a procedure, the way the arms, consoles, tower are set up. Because temporary setups or incomplete configurations of the system will create invalid results. Environmental factors such as space, power stability, and network connections, these also matter. You always need a calm, organized setup, which leads to more accurate, smoother verification results, more reliable results. So it's always good to be prepared before a PVK. Early PVK steps focus on system power and startup behavior. So engineers can verify that the system powers correctly, that the backup system of the HUGO tower behave as expected, and that there are no unexpected warnings or alarms during boot. These checks confirm more than basic functionality. They validate that the power distribution is working, the communication between the subsystems are working, and the system's ability to enter a safe operational state. Skipping or rushing these steps can allow hidden issues to appear. The PVK is designed to surface these problems under controlled conditions rather than during live surgery. A major portion of the PVK focuses on robotic performance. Engineers verify that each arm is able to move smoothly, accurately, within limits. Sensors, encoders, and safety features are indirectly validated through these checks. Once you perform the arm, you're also checking the sensors and the safety features all at the same time. And consistency matters. All arm carts must behave predictably and in alignment with each other. They are not about how fast you can do it, about the speed. It's about confirming that the system will respond precisely to surgeon input during live procedures. Here we are in the console, the surgeon console. So the surgeon console is the primary human interface to the HUGO system. During PVK, engineers verify that inputs from the hand controllers, the pedals, and displays are all correctly interpreted by the system. This includes checking visual overlays, system indicators, and the response timing of the device. And any mismatch between the input and the response can undermine surgeon confidence and safety. So engineers need to approach this step very carefully and methodically. The PVK ensures that what the surgeon sees and does at the console translates accurately to robotic movement at the patient side. PVKs intentionally test how the system responds to abnormal conditions, anything that you don't expect. Engineers verify that the alarm trigger correctly and that the system enters already known defined safe states when required. And equally important is recovery as well. The system must be able to return to normal operation in a controlled manner after an alarm or a pause. This confirms both safety and usability as well. These checks demonstrate that the system prioritizes patient protection over continued operation. which is a very fundamental design principle in surgical robotics. Almost finishing, which is the documentation and the sign-off of the PVK. This is what all engineers must do with any device. Completing the PVK is not the end process, of course. Engineers must accurately document the results. They must record serial numbers, complete any required sign-off steps. What's the purpose of this? Is to provide traceability and also accountability. From a regulatory perspective, documentation is as important as the technical checks themselves. Incomplete or inaccurate records can invalidate the entire PVK. Engineers should treat documentation as part of patient safety, and clear, accurate records protect clinicians, they protect the patient and the engineers also who perform the work. What are some final takeaways? A HUGO performance verification check is not just a technical exercise. It's a very structured, methodical process designed to build trust between the engineers, the clinicians, and the patients. Every step exists for a reason, and following the process carefully ensures that the system behaves predictably and safely when lives are on the line. So for engineers, PVKs reinforce professional discipline. They remind us that in medical technology, how we work is just as important as what we fix. And understanding and respecting that responsibility is what defines a true medical device engineer.